Good day, ladies and gentlemen. We are all welcome back to our lecture number 3 on electronics engineering, that is Eeen202, which deals with 3 aspects: electronics, measurements, and transducers. And if you can remember, in our lecture number 2 we have discussed how PN junction diodes was formed. That is, we have a piece of pure semiconductor device like silicon or germanium, and we introduce group 5 elements through one end, and we introduce group 3 element to the other end. And in this way, the segment or the section where we introduce group 5 element, it is N-type semiconductor, and the other one to which we introduce group 3 element, it is P-type semiconductor, so that we have PN junction diodes. And in that lecture I also explained the characteristic curve of PN junction diode, where we have seen that when the diode is forward biased, it conducts, but the conduction is not starting immediately. There is a minimum value of forward bias voltage that will make the diode to start conducting. The moment that value is reached, the current of the diode will now start rising exponentially as the voltage increases. So now, since we know the basic pure semiconductor devices we use are either germanium or silicon, as we have seen in our first lecture, so this graph is now a combined characteristic curve of PN junction diode, the one that is made using germanium and the other one using silicon. And if we look at this carefully, in the forward bias direction, we can see that the minimum voltage for germanium diode to start conducting is 0.2 volts, and this minimum voltage is what we call cut-in voltage or turn-on voltage of the diode. And for the germanium, for the silicon, the value is 0.7 volts. So you can see that the conductivity of the germanium is higher than that of the silicon. We have already seen this one in our graph of group 4 element, where we have carbon at one end as insulator, tin at the other end as conductor, and the silicon and the germanium are in between. But that the energy gap of the silicon is larger than that of the germanium. So now what we are saying here in essence is that whenever you forward bias PN junction diode made from germanium, you need 0.2 volt before it start conducting. The moment that voltage is reached, the current will now start rising exponentially with respect to the voltage. For the silicon, it needs 0.7 volts. But we have already also explained that we can either forward bias diode or we can reverse bias it. So in the reverse bias direction, for an ideal diode, we're supposed to have a zero current flowing. But as I told you, we have minority carriers in the PN junction and what in the N in the P region and in the N region. And when I reverse bias it, these minority carriers, they will now be crossing the junction, and as a result, a very small amount of current will start flowing. And when that current start flowing, we call it a reverse saturation current. And as we can see here, as you keep on increasing the reverse bias voltage, you are going to take this PN junction to what we call a breakdown voltage. What is the breakdown voltage? It is the voltage at which the reverse bias PN junction diode will now start conducting in such a way that the current will keep on increasing continuously without any increase in the value of the voltage. So we can see here the breakdown voltage for the germanium is less than that of the silicon, but the moment the breakdown is reached, the current will keep on increasing in the reverse mode while the voltage remains constant. Now, with respect to what we have seen, we said when the PN junction diode is reverse bias, it reaches a point we call a breakdown voltage, and that is when the currents start increasing continuously without any increase in the value of the voltage. So with respect to that fact, we have two breakdowns. we have what we call avalanche breakdown, and we have what we call a Zener breakdown. What is the avalanche breakdown? The avalanche breakdown is brought about by the minority carriers. Whenever you increase the reverse voltage, we reach a point where the diode start conducting current in the reverse mode without any increase in the voltage. And what brings about that is the collision of the ions in that crystal in such a way that more mobile carriers, electrons, and the holes are created whenever that voltage increases. And as this collision increases, we have a very large amount of current that will start flowing through the reverse mode. And this process of increasing the reverse voltage, which increases the collision of the molecules in such a way that more charge carriers are generated and current keeps on increasing, we call it avalanche multiplication, and it occurs at the knee voltage, and the knee voltage is greater than 5 volts. Then we come to the other breakdown, which is the Zener breakdown, and this one also, it has to do with what? The reverse bias mode of a diode. Whenever you keep on increasing your reverse voltage and it becomes a bit stronger, we reach a point where the electrons are now forcefully broken from their bonds. And whenever you break these electrons from the bonds, they are creating holes. So as these more minority carriers are breaking from their bonds, creating electrons and the hole pairs, we reach a point where the current keep on increasing continuously. And if that happens, we have what we call a Zener effect, and that Zener effect takes place whenever the reverse voltage reaches the minimum amount of voltage to cause that Zener effect, and the voltage is always supposed to be less than 5 volts. We can see the difference. For the avalanche breakdown, greater than 5 volts. For the Zener breakdown, less than 5 volts. Now, these two effects, that's the Zener and the avalanche breakdowns, they can occur separately. That is either Zener to occur or the avalanche to occur separately. And sometimes they can occur together. That is both the Zener and the avalanche breakdown taking place at the same time. And how do we know when they occur separately and when they occur at the same time? Whenever your voltage is less than 5 volts, only Zener breakdown can happen. When it is above 5 volts, only avalanche breakdown can happen. But if the voltage is exactly at 5 volts and the breakdown occur, then it is the combination of the two. That is the avalanche and the Zener breakdown. If we understand this, we now come and define some important terms in respect to PN junction diode. The first thing is what we call diode breakdown voltage. What is the breakdown voltage? This is the value of the reverse voltage applied to a diode which is reverse bias, at which the junction of the diode is destroyed. That is, the current continue to flow without any increase in the voltage. That is what they call the diode breakdown voltage. The next term is what we call knee voltage or cut-in voltage. And what is it? It is the forward voltage at which the current through the junction starts to increase rapidly. That is, the moment you reach that minimum voltage, the cut-in, the current will now start rising exponentially. The third term is what they call peak inverse voltage, PIV. And what is it? It is the maximum voltage that can be applied to a PN junction diode in the reverse bias mode without damaging the diode. Thus, the moment you apply a voltage in the reverse mode above the peak inverse voltage, a breakdown can occur. And what is the next term? Is the maximum forward current. What is the maximum forward current? It is the maximum instantaneous forward current that the PN junction can withstand without destroying the junction. What are we saying? We are saying the amount of current that can flow when the diode is forward biased, it has a limit. The moment you supply more than that current, the junction is going to be destroyed. And the fifth term is what they call maximum power rating, and this is the maximum power that the PN junction diode can dissipate. That is the product of the voltage and the current it can withstand. If you go beyond that, you are going to destroy the diode. Now, if you understand this, the next thing we're going to look at are the applications of the diode, and the diode is used in different forms of applications. One of them is what they call waveform shaping. That is, we use diodes for generating different waveforms, sinusoidal waveforms, triangular waveform, sawtooth waveform, square waveform, and all the other types of waveforms. And also we use it for switching, that is on-in and off-in systems. We also use diodes in logic circuit, that is in digital electronic systems. It is also used in television set, in FM receivers. It is used in amplifiers of different types, and these amplifiers can be of radio frequency, they can be of audio frequency. Now we now come to one specific application of a diode, which is voltage rectification. What is rectification? A rectification is simply a process where a sinusoidal waveform, which changes between positive and the negative directions, is now changed to flow in only one direction. So the process of changing bidirectional waveform to unidirectional waveform is what we call the rectification. And we have different types of rectification. We have half wave rectification and we have full wave rectification. So what is the half wave rectification? And we define this as the rectification process where the diode allows only positive part of our alternating signal to pass and block the negative. And in the same time, if we wish, the half wave rectification can be a process of what? Allowing negative to pass and blocking the positive. Therefore, it allows only one polarity, either to allow positive and block negative, or allow negative and what? Block positive. And the reason why it does that is that the diode is conducting in only forward bias mode, and when it is reverse bias mode, there is no way it can conduct. We have already discussed this one intensively. Now, to understand what we are saying, let us look at these two graphs. This is a typical graph of sinusoidal waveform which alternate between the maximum and what? Negative, maximum positive and maximum negative. Now, the rectifier, as you can see from this diagram, it is made using a diode. This is the source of my AC signal, alternating current signal, and this is the load where I deliver the output of the diode. Now, when this alternating signal is coming along this positive direction, my diode is forward biased, and therefore it will allow everything to pass. When the negative comes, the diode is now reverse biased. It will block it, meaning it will not allow the segment to pass. When the next positive comes, it will be allowed to pass. The next negative is what? Block. And if you look at this, we are allowing only one polarity and blocking the other one, and that is why we call it half wave rectification process. Now the next thing is to look at what we call the full wave rectification process. And in this full wave rectification process, both the positive and the negative waveforms are passed, but they are passed in only one direction. And we achieve full wave rectification using either what we call a bridge rectifier or using center tap transformer method. And now let us discuss them one after the other. This is what we call the center tap transformer methods. I have two diodes, D1 and D2. Now when the positive signal is coming, this my terminal A is positive while terminal B is negative. Therefore diode D1 will conduct, but diode D2 will not. When the negative is coming, then the polarity here will change. This will be negative and this will be positive. When this is positive, diode D2 will now conduct and D1 will not. And the output of this D1 comes this way to the load, and the output of D2 also comes the same way to the load, meaning what D1 and D2 are conducting, they are now flowing in the same direction, because their output have been delivered to the load in the same direction. So what we have here is that my positive is passed, my negative is passed. The only thing is that the negative has been changed into positive polarity. This is a full wave rectifier using center tap transformer. Then the second type is a full wave rectifier that uses a bridge. A bridge of how many diodes? 4. We have D1, D2, D3 and D4. Now what we need to look at is that when the positive half is coming, this point should be positive and this one should be negative. So when this is positive, you can see that this diode is reverse biased because this is my cathode, but this one is forward biased because this is the anode. Therefore diode D1 will conduct, but the negative that is coming here, it will reverse bias this one and forward bias this one, meaning in the first half cycle diode D1 will conduct to the load and my D4 will also conduct to the load, and it will be in this positive direction. Then when the second half, that's the negative polarity, comes, the polarity will now reverse. Here should be negative and here should be positive. When I have negative here, this diode D1 is not conducting, but diode D3 will now be conducting to the load, and at the same time when this is negative, this one should be positive, and therefore diode D2 will not be conducting, but D4 should be D4 will not be conducting, but D2 should conduct. Therefore in the other half cycle, D3 conduct to the load and D2 also conduct to the load in such a way that they flow in the same direction with the other one. So what we have done in essence, we have changed all the negative polarities into positive, but all of them are passing but only in one direction, and that is what we call full wave rectification process. Another application of a diode, we use it in what we call voltage doubling circuit. And the voltage doubling circuit, if you look at it, it very much resembles our full wave bridge rectifier, but the only difference is that instead of having 4 diodes in the bridge, we have 2 diodes together with 2 capacitors. And how does the operation takes place? When the half cycle of the signal comes, here should be positive and here should be negative. When here is positive, diode D1 will be conducting, but D2 will not be conducting. When D2 is not conducting, whatever energy comes here will be charging this capacitor. And in the reverse mode, here should be positive and here should be negative. If here is negative, D1 will not be conducting, therefore capacitor C2 will be charging, and here D2 will be conducting. So when D2 is conducting, the energy stored by the C1 in the previous half cycle will now come out together with what this diode is conducting, therefore they should be twice, and that is why we call it doubling circuit. And also when this one starts to conduct, the voltage stored in this capacitor will be coming out, so the two of them will reach the load, so that the twice of the supply voltage will be experienced at the load, and this is what we call the voltage doubling process. Now another application of a diode is what we call clipper, and these clippers, they are also called limiters, and sometimes they are called amplitude selectors. And the function of this clipper is to eliminate part of the waveform that is above the reference point or that is below certain reference point. And generally we use this clipping circuit for transmission of the message, so that we limit the message to the amplitude we want. Anything above that should be truncated, should be cut out. And how do we achieve that? We use diodes together with a battery in series, and they should be connected across, that is in parallel to our supply. Let us assume this is my input signal and this is my diode together with the battery, and my clipping circuit operates like this. When this signal is coming, it will be forward bias this one because here is positive, so that the diode will start conducting, and whatever is this diode is conducting will be seen at the output terminal. But the moment this voltage become equal to the voltage of this battery, which is the reference, then the diode will stop conducting and will not see anything here. So here is a typical a graph showing the operation of a clipper, meaning when this voltage is coming, it should keep on increasing until we reach the reference voltage, which is equal to the voltage of this battery, and anything above that should be truncated, should be cut out, so that everything above this reference should not be seen at the output. And when it is coming down, everything is allowed. The moment it reaches the reference again, it will block that portion and it starts going to the low. Now the next thing is the diode application as a clamper, and this clamper is just a circuit that has the ability of shifting the waveform. This time around, it is not going to cut it, but it is going to shift it, that is to rise it off or to lower it below certain value. And how does it do that? It does it by using three elements. Generally, we have a capacitor which is in series with our supply, we have our diode in parallel to the supply together with a resistor which is in parallel with the supply. Now what happens is this: whenever this voltage is coming, it will be charging the capacitor, and at the same time this is allowed to be going out. But when the negative comes, when the capacitor is fully charged, nothing will go out. That is, this positive will charge the capacitor, it will allow the signal to pass, but whenever the negative is coming, the diode will block it. So when it is blocking, it means, you can see this is my input. The input has a maximum of 1 and minimum of -1. So now when the positive is coming, it will be charging the capacitor, and what is stored in this capacitor will now be coming out together with the signal of this, and they will be going out. So therefore the capacitor will store the maximum value, which is 1, and this diode will be conducting that 1. So 1 plus 1 should give me 2, and that's why my output here is maximum of 2. But when the voltage started going to the negative, my diode will be reverse bias, therefore it will not be allowed to go below 0. So what we are doing here is like we are shifting the level, because you can see the interval between +1 and -1 is equal to 2, but here instead of allowing to see +1 and -1, we shift it upward so that we can see the maximum of 2 all in the positive direction, and that is what we call a clamper, which is one of the applications of the diode. Then another type of diode apart from the ordinary PN junction diode we have seen is what they call Schottky diode, and this diode is constructed with metals like platinum or aluminum, and it is fabricated using N-type or P-type semiconductor as illustrated here, meaning we don't use P and N-type semiconductor, we use only one type, either P as our channel through which the signal will be flowing, though we have the N-type here below, P-type below the N channel, but this one we call it substrate, and this substrate is nothing but the base on which the whole diode is fabricated. And my contacts here are 1 and 2, and the 1 stand for my anode and the 2 stand for my cathode. And you can see this figure or this symbol is what differentiates the Schottky diode from our ordinary diode, which doesn't have these bendings. And this diode is used mostly in integrated circuit technology. Why? Because it is easier to be fabricated in form of IC together with other components, and it has many applications, which include it is used in high frequency switching applications, it is used in power monitoring of low level radio frequencies, and it is also used in detecting high frequencies. All these things, high frequency switching application, power monitoring, those of you that would be in electrical engineering or are in electrical engineering, you're going to learn them in details at further levels starting from 300 level. Now another type of diode is what they call light emitting diode, and according to this name we can understand that this diode produces light as its output, meaning it accepts electricity as an input and produces light as an output. And how does it produce the light? It produces the light based on what we know from our basic physics, we know, or chemistry rather, you know, there is what we call ground state energy of an atom, and there is what we call excited state energy. And the energy pulses in these two levels, they are called ground state energy and the excitation energy, or energy of excitation. So whenever an electron absorbs extra energy either from heat or from electricity, it can jump from its normal shell to the higher one. And in this case, we are saying it should jump from the valence band into the conduction band. But if it goes there, there is every tendency it will not be there forever. It will fall back into its valence band, and in trying to do that, it has to lose the extra energy it has absorbed, and this energy is the one that is changed into light energy. And it is very important for us to know that the light emitting diodes, they can produce light only when they are forward biased, and the intensity, the brightness of the light they should emit or they can emit is directly proportional to the magnitude of the forward current. That is, whenever the forward voltage increases, the forward current also increases according to Ohm's law. And when the forward current increases, the brightness of the light produced by the LED light emitting diode will increase. Here is the circuit diagram. This is my battery and this is my p-n junction diode. You can see the positive pole of the battery is connected to the p terminal and the negative is connected to the n terminal, and this is what we call forward biasing. And this p-n junction diode, we can now replace it with this symbol. You can see two arrows pointing outward, meaning it is producing light as an output. And I also said the magnitude of the light, the intensity of the light, is directly proportional to the forward current, meaning whenever the current is increasing, you can see that the light is rising according to this graph, and that is what we mean by they are directly proportional to one another. Now, the LED, that is light emitting diode, has so many applications. One of them, it is used in systems display. Whenever you want a light to be blinking in order to show something or to stay constantly showing, indicating the presence of power or something, we use it for that purpose. It is also used in optical fiber communications. Those of you in electrical engineering, computer engineering, telecommunications will learn more about this at the higher levels. They are also used in infrared remote control. They are used in security alarm systems, and there are many more applications of light emitting diode. These ones are just few as examples. Now, the next thing is what they call 7-segment display, and this 7-segment display is nothing but a device or a component that is fabricated using 7 different LEDs, and all these LEDs, they are arranged in such a way that they can indicate figures from 0 to 9, and they are connected in such, mostly they are connected in common cathode configuration. What we mean by common cathode is that all the cathodes are connected together. All the cathodes are connected together, and the anodes are excited in such a way that whenever you apply a current or a voltage to the anode of any of the diodes, it will bring a light. Look at this example, please. Here I have 7 of them, and I label them A, B, C, D, E, F, G, and all their cathodes are connected together to the ground, but the anodes, they are separately excited. And these 7 diodes, they are arranged in this. This is my A, this is my B, this is my C, this is D, E, F, and this is G. And as you can see, whenever these B and C are on, I should have something representing 1. And whenever all of them are on, you can see that it is a figure 8. And when A, B, G, E, D are on, this is 2. So therefore, depending on which ones are on, it will display numbers from what? 0 to 9. Supposing A, B, and C are on, this is 7. So therefore, 7-segment display is a kind of diode that contains 7 LEDs connected in such a way that they can display numbers from 0 to 9. The next thing is two color LED emitter. You know, light emitting diodes, normally they produce one color. They should be either of color of your choice. They can be green, they can be yellow, red, anything. But sometimes I know some of you have seen where you see the same light emitting diode changing colors, especially in our universal chargers of GSM handsets. Now this is a typical example. As you can see, I have three terminals, A, B and C. This is contrary to the one we have already seen where we have only two cathode and anode. So now the color of the light to be produced by this LED depends on which terminals are triggered. Whenever these terminals B and C are on or are connected to the supply, a red light is produced. Whenever A and C are powered, the light is green. And there are other types of LEDs that can produce more than two colors depending on how they are powered. So if you understand this, the next thing is to look at what we call photodiode. And this photodiode is a kind of diode that accepts light as its input signal and produces electricity as the output. And if you look at this one, it is exactly performing the opposite, the inverse function of what the light emitting diode, because the light emitting diode takes electricity as an input and produces light as an output. But in the opposite, this one takes light as input and produces electric current as the output. And for you to operate it, you have to make sure that you reverse bias it, because if it is forward bias, it will just be operating as any ordinary diode. Therefore, we have to reverse bias it, and we have to take it to a point where our reverse saturation current is controlled by the intensity of the light falling on the diode. And these lights create electron hole pair, meaning the light is a form of energy. It will now be breaking bonds in such a way that electrons and holes are created. And you know, whenever these charge carriers are produced and they are flowing, a charge is flowing. Whenever there is charge, then there is current, because current is equal to charge over time. And the amount of current it can produce is directly proportional to the intensity of the light. The higher the intensity of the light, the more the current it can produce. And it also acts as a constant current generator, meaning it can supply you with a fixed value of current the moment we reach what we call breakdown, because I told you we have to operate it in what? Reverse bias mode. So once we reach breakdown, the voltage will remain fixed while the current will keep on changing. The voltage will remain fixed while the current will be the current will remain fixed. That's the meaning of constant current generator, and the breakdown voltage is already exceeded. Now, the sensitivity of this diode to the light, we can increase its sensitivity by making the junction area larger, so that while the area of the junction is very large, it has tendency of collecting large amount of what? Light energy, and for this reason it will produce a very large amount of current. Thereby we say it is what? Highly sensitive to the light. This is the typical block diagram. As you can see, this my arrow is now pointing inwards, meaning light is serving as an input. And if you look at this diode, I connect my negative to the P terminal, and I connect my positive to the what? N terminal. This is my anode, this is my cathode. And of course, you know, this is a reverse bias mode. And in reverse bias mode, ideally we are not supposed to have anything like flow of current, but because of this light falling on this junction, it creates pairs of electrons and holes. Thereby when they move, they create a current. And this graph is now telling me the intensity of the light, its influence on what? The amount of current. Now if you look at this, this is H0, where I have the lowest intensity, and the amount of current, you can see it is crossing zero line. When you keep on increasing maybe to a certain value, the reverse current is increasing very much along the negative axis because of the increase in the light intensity. So The next type of diode is what they call a Zener diode. You can remember we discussed what we call Zener breakdown. This Zener diode is a diode that has a characteristic. It has ability of maintaining a voltage at a fixed value despite the variation in the source voltage and the variation in the load current. Meaning, even if the current load is increasing or decreasing, even if the source increasing or decreasing, the output voltage will remain fixed, and that is why we use it as a voltage regulator. And it is made of PN junction diode by doping the material to produce very steep. If we say something is very stiff, in this sense we mean it is very strong. Before the avalanche breakdown takes place, it can tolerate a very large amount of stress from the voltage supply. And the reason why we make it very steep is that we want to prevent the diode from being damaged when the breakdown voltage is exceeded. Therefore, we make it steep in such a way that it will remain at that breakdown voltage. And this condition is true only if the maximum rated current of the diode is not exceeded. Supposing you have a diode that the manufacturer said it can take maximum of 1 ampere when it is at the breakdown voltage. When you load it with more than that, it can not operate the way you expect it to. And for us to understand the operation of the Zener diode, let us look at this graph. As I told you, when the diode is reverse bias, ideally we are supposed to have zero current. But as you keep on increasing the value of the reverse current, reverse bias voltage, you reach a point where the rate at which the bonds are broken is increasing rapidly, and this pair of electrons and the holes created from this breakage of the bonds will now bring sudden increase in the value of current while the voltage remain constant, and that is what we call the Zener voltage. Now, we use a Zener diode, as I told you, as a regulator. That is a device that will fix our voltage constant even if the current we require at the load is changing or the supply from the source is also changing. And this is how we connect it. We have our source of the voltage, and we connect this Zener diode across, that is in parallel to it. The reason why we connect it in parallel is that whatever is the voltage across this diode should be equal to the voltage to the load, because if two things are in parallel, they have the same voltage, and this is the resistor that controls the amount of current flowing. And if you look at this, if I want to find the expression for my input resistance, this I would like to say it is what the potential difference between the terminals, which is the voltage supply, minus what the voltage drop across the Zener diode or across the load, because they're in parallel, they have the same voltage, all over the total current. And the total current is the summation of the one going to the load and the one entering the Zener diode. And that's why I say Ri, the input resistance, is equal to Vs minus Vz, was the potential difference between the resistor all over the total current. And if you take this current to this side and input resistance to this position of the denominator, and you simplify, you are going to get the expression for your Zener current equal to this. And as I have already told you, the load current do changes and the supply voltage also changes. Now, if we want to find the value of the Zener diode when it is, Zener current when it is at maximum, we can reach that maximum value when my supply voltage Vs is maximum and my load current is minimum. But if I want to get the minimum value of my Zener current, it is obtained when the Vs supply voltage is minimum and my load current IL is what? Maximum. Now, substituting these two conditions, I have these two expressions for the maximum value of my Zener current and the minimum, and each of them, they are equivalent to the input resistance, meaning I can equate this expression and this because all of them are equal to Ri. And equating them, I have something like this. For me to simplify and get the expression for my maximum Zener current, all I need to do is to say we assume the minimum Zener current is 10% of what the maximum, and if you substitute it here, finally you make your Zener current equal to this expression. Meaning, if you want to find your Zener current, all you need to do is to know the Zener voltage, to know the maximum supply and the minimum supply, and also the maximum load current and the minimum load current. You can substitute and get the value of your Zener current at its maximum value. So at this point, ladies and gentlemen, we come to the end of our lecture number 3, and I'd like to thank you very much for your time, and I encourage you to watch over and over again. If you have anything that is not clear from this lecture, feel free to come and contact me for clarification. Thank you very much. Meet you in the next tutorial.